Good evening, everyone. A warm welcome to all the participants joining us from across the world to the day 4 of our 6 days International Faculty Development Program on a pragmatic exploration of threat intelligence using edge and quantum computing tools, bridging academia, industry, and teaching practices. We are delighted to connect with you virtually from RMK College of Engineering and Technology, a proud AICTE approved autonomous institution affiliated with Anna University and recognized as an ISO 21001-2018 Center of Excellence. So this FDP meticulously organized by Department of Computer Science and Engineering in collaboration with Computer Society of India exemplifies RMK's unwavering commitment to empowering faculty, fostering global collaboration, and nurturing academic excellence, guided by the visionary leadership of Thiru R.S. Munithatram and Thiru R.M. Kishore. Over the past 3 days, we have explored threat intelligence, edge computing, AI-driven security, and machine learning applications. Today, in the day 4, we are moving into the emerging domains of quantum computing and post-quantum cryptography, exploring next-generation computing paradigms and future-ready cybersecurity solutions. It's my great pleasure to introduce our distinguished speaker of today's session, Dr. Indra Priyadharshini, Assistant Professor Senior Grade in the School of Computer Science and Engineering at VIT University, Chennai. Dr. Indra Priyadharshini holds a PhD from Anna University and brings over 20 years of experience in teaching engineering students. She is a passionate educator who enjoys mentoring young minds, taking on challenges, generating innovative ideas, and guiding research projects. Her academic and research expertise spans network security, cloud security, cryptography, and health clouds. She has made significant contributions to advancing secure computing practices and has actively participated in consultancy projects, curriculum development, and academic outreach initiatives in cybersecurity and emerging technologies. Today, Dr. Indra Priyadharshini will be delivering two insightful sessions. In session 1, we are going to see about quantum computing fundamentals for faculty, which includes concepts, algorithms, and pedagogy. And in session 2, the session 2 will be in the topic of post-quantum cryptography, and there the covering subtopics will be industry roadmaps, standards, and security implications. Her dedication to teaching, research, and innovation has made her a respected figure in her field, and we are honored to have her share her expertise with us. Please join me in extending a warm welcome to Dr. Priyadharshini, and I hand over the stage to you, ma'am.
Thank you so much, sir. Thank you so much for that nice and kind introduction. I would like to thank the management of RMK, College of Engineering and Technology, the head of the department, and the coordinators, Dr. Shami Fatima and Dr. Indra for inviting me for this meeting. When I think about RMK, like I'm relating to my inspiration, I'm always grateful to the management of RMK, the examiners management of RMK. Thank you so much for this opportunity, and I would like to appreciate all the participants who have joined today. Even after the office hours, the dust of knowledge, I would like to appreciate your dedication and determination for learning something new. So, without wasting time, let me start my screen. My throat is a little bad. My voice might sound a little weird. Yeah. Hope the screen is visible and my voice is audible.
Yes, ma'am, your screen is visible, ma'am.
Yes. Thank you.
Okay.
Yeah. If you guys have heard the introduction correctly, you could have guessed my research area. I'm into security. All my research works are in network security. Okay. Yeah. Is the voice audible now? Is the voice audible?
Yes, ma'am, it's audible.
So, like, I'm basically into the field of security. My Indian research is in network security and cloud security. I have started my body using quantum because since the entire world is moving towards quantum, I have started incorporating quantum importance into the field of security. Because this post quantum security is a buzzword everywhere. So, so I'm a budding researcher in quantum computing. So let's start the session. I brought this diagram just to indicate that quantum computing is not a very new word. The diagram shows that early quantum science is from the early 1900s. Now, the evolution from 1900 to the recent modern quantum computing technologies. So, it started with the theoretical breakthrough from the quantum hypothesis of Einstein's photoelectric effect, Schrodinger wave mechanics. That it shaped the understanding of quantum mechanics. So, this discovery of quantum entanglement and all the discoveries in physics, in the field of physics, it has laid the groundwork for the computational applications. If you see the lower mark diagram, Feynman's proposal of quantum computing, there started, in 1900, it started there. It laid the foundation for the major algorithmic breakthroughs. So when Google says about quantum computing, the first word you will get about quantum computing is Shor's algorithm, Grover's algorithm. All that it started from the Feynman's proposal in 1900. So, this timeline shows us from one century, scientific years have evolved and it is taken a lot of practical efforts. Now we have achieved what we have achieved in quantum computing. So, with this introduction, let's get into the actual quantum computing. What is the need for quantum computing? Why we are going for quantum computing? So, in today's world, there are increasingly hard problems. There are wide variety of problems that today's computing can solve. But there are certain set of problems that today's computers cannot handle, or it might require more amount of space and time to handle such kind of problems. So, there comes the field of quantum computing. To understand this, what is hard problem, what is easy problem, which problem needs quantum computing. To understand that better, I took this graph. So here, if you look at the x-axis, we have input sizes, different types of size of inputs you can give to a problem that is being plotted. And in the y-axis, the amount of time and memory a particular function or particular program can take. It is in y-axis. And I just plotted a very simple polynomial function that runs in linear time n, and there's a quadratic function n square, and there's an n function. So when you look at the graph, the curve is very steep. Then you can consider that problem as the harder problem. Harder in the sense it might take more amount of time or more amount of resources to run. So when you look at this graph, you can see that the linear function n is not super at all, right? It's not super at all. And you can see that the quadratic function in square, it is looking little steeper, which means it as as it grows, more time and more amount of money is required. More amount of memory is required. So now to add some more masala, let's add some more functions. So I have added one more polynomial function, one quadratic function, and two exponential functions, which are n and k. So now when you look at the graph, you can see that both the exponential functions for n and phi bar n flag the left hand side of the graph. So I won't go over the left hand side. Very steep. Really, it shoots up the moment you start the graph. For very less size of inputs, it is shooting fine. And you can see that n square is still in curve. And you as usual, we leave the function n and n is always very. Therefore, we understand that exponential functions are, it is not even tractable in classical computers. The amount of time, the amount of memory required for running exponential functions, it wouldn't track better in classical computers. So, like when I expand my y-axis further, when I increase the span of my brain, Now this graph, the linear function is not even, it has disappeared. The n log n function is almost very flat. And you can see still the exponential function and the deeper polynomial function, deeper quadratic function in the top right, are still at the left hand side. Therefore, the quadratic, the degree of the quadratic function is more part of the exponential problem or the exponential function. Very sliding towards the left hand side, and it is very steep. Therefore, we could not actually classify. Very interestingly, if I change my y-axis to the log, instead of linearly increasing my y-axis, if I put it in the log scale, the linear functions or the log n function are disappearing. You could even see that the n square polynomial is also not like that. Therefore, if it is seen in the log scale, those functions are really, really fast. Even if the input is very large, those functions are very fast. But still, the exponential functions are steeper. And n to the power 5 is slightly slow. Okay. So now to add some more on this, we are further decreasing timeline. Now you can see all the polynomial functions are not seen because when you increase the time input logarithm factor, that factor, if the amount of time is very quick for the quadratic functions or the linear functions or the n log functions, so it would not be visible in the graphic part. But you can see that the exponential functions are just similar to whatever state it was in before when I started the graph. Therefore, this kind of exponential function which require or which grow in terms of exponential, in terms of time or space required, it could not be tractable in the classical computers. That is what I'm trying to convey with these graphs. So the problems which are growing in exponential terms are not tractable with classical computers. Therefore, it would be difficult for a classical computer to execute also. Isn't it? So that's where the quantum computing need comes. So now if I move it further to my left hand side of the graph, if you look at the starting stage, when the inputs are really smaller, you can see that the quadratic functions are even dominating in exponential functions when the input sizes are small. You can see that x to the power 5 is dominating the exponential functions when the input sizes are small. Which means what? Which means if the input sizes are smaller, the polynomial functions are behaving very bad than the exponential functions. So in the previous slide I told you, the exponential functions are not tractable in the classical computer. So quantum computing is needed. And when I see more further down, I see when the number of inputs are very less, the polynomial function is equally behaving bad, just similar to the exponential function. But sometimes it behaves very bad than the exponential function. So to put it in very crisp terms, if the input sizes are small, the polynomial functions are even dominating the exponential function. So therefore, if the polynomial sizes are small, even for the exponential function, classical computers will do a good work than a quantum computer. So I'm trying to tell you, the input sizes are very small for exponential function or for the polynomial function. Classical computer can perform better than the quantum computer. So we cannot conclude that quantum computing is the best computing, but quantum computing is good to suit all kinds of problems. If the input sizes are small, if the degree of the polynomial is different, or if the nature of the polynomial is different, it would be. So quantum computing would suit quadratic problems. And if there is an exponential problem, quantum computing is a promise that running exponential problems in a more sophisticated way than the classical would. That is the takeaway of this graph, execution time, space complexity, comparison of different types of problems. This is the takeaway. So we need quantum computing to solve these exponential problems, but you can't generalize that. Certain problems are good with classical. Right. So that's what I'm trying to tell you. So now let's go to. I thought of comparing classical. All these slides, the content I have taken from IBM. you go to IBM, because it's just IBM company, you will get these open source learning. There are a lot of data in IBM platform where you can you can even test it in quantum algorithms, quantum circuits, in discrete open source. So I took most of the information from IBM platform. Uh, yeah. So I was comparing classical computing with quantum computing so that most of the time computer science programmers we could relate it with classical. So let's start with we know that in computers everything is zeros and ones. We have determined the states 0 and 1. So it's the states are very determined, either 0 or 1. And we know the don't need or only generate. So when we come to quantum computing, we call it here as states. Is there a message? Okay. I think there is no problem for my side. Is my voice clear?
No, no. Yeah, no.
Okay.
Breaking voice.
My wife. Okay. My voice sounds that. Like is it at least louder? Is it at least louder? Okay.
Louder, but it's very noisy.
Okay. Let's stop this. Okay. So now is that okay? Okay. Okay, ma'am. Okay. Right. Okay. Let's again start. So quantum computing we use operational qubits. Qubits are these fundamental quantum bits. So it is not determined. And just like classical computing, it is not definite. It is not just 0 or just 1. It could be combination of 0 and 1. Okay. Thanks. Right. So in quantum computing, the bits 0 and 1, generally we will represent them as unit vectors. Let me see what is unit vector. Hope you all of you know what is a vector. No, this fundamental of quantum computing is a lot more about physics and mathematics together, quantum mechanics together. It might sound a little weird and little tough in the beginning, but when we practice the problem or when we practice the problem, it would be understandable. Even for me, when I listened for the first time, it was difficult. So we can understand it because we go to our yeah. So quantum states are continuous. It's not definite 0 or it's not definite 1. It could be a linear combination of 0 and 1. I mean, it could be both 0 and 1. That's the specialty of quantum computing. We call them as superposition. Now look at this. Yeah. And you take this one. You can see it is a linear combination of 0 state plus 1 state. So this alpha amount of 0, amount of 0, it could be. We call this alpha and beta as probability amplitude. It is not the actual probability. It is probability amplitude. And it is most of the time it is complex numbers. It is a complex number. Alpha and beta are complex coefficients. So this state is called a superposition state. So in classical computing, the bits can either be either 0 or 1 as a value. In qubit, it could be 0 state or it could be 1 state or it could be linear combination of 0 state plus 1 state. So based on the probability, you can measure what is the output of that state. What is the actual value of that state, you can measure. Only if you know accurately what is the probability. So if you know the coefficient values in alpha and beta, then you can calculate the probability of when it will be 0 or when it will be 1. So when you look at the last paragraph, this one, you can see the probability of a state to fall into 0 state is not as small. The probability of a state to fall into 1 state is bigger. What we know. So if we know the coefficients of alpha beta, then we can calculate the output. So so in classical computing, the theta determines it is definite. It's going to be either 0 or 1. But in quantum computing, a state Q or a qubit Q, it could be a linear combination of uh, 0 state plus 1 state, alpha amount of 0 plus beta amount of 0. This notation we call it as state. This notation we call that as state. Sometimes we call that as state, or sometimes we call that as 0 qubit, 1 qubit, or sometimes 0 state, 1 state. All these are interchangeable. So, basic representation, the basic integration in quantum computing is qubit. And the qubit could take either the 0 value or the 1 value, or it could be both 0 and 1. So, a combination of 0 plus combination. So, we can measure the output of that state by measuring that state. So, for measuring that, you will need the probability amplitude and theta, wherever you measure, and you can see the result. So, already so, next comparison is comparing the computation method. In classical computing, the framework which we use for doing digital computation is Boolean algebra. And we know what is a Boolean gate. The function of the Boolean gate is represented as a Boolean gate. So, the example gate that I have taken here is NOT gate. All of us know what is a NOT gate. So, whatever input we give, that gets complemented into output. Not 0 is 1 and not 1 is 0. So, the equivalent gate in quantum computing is called polyexchange. We call that as polyexchange. So, in classical computing, we represent a function of Boolean gate as a Boolean algebra. So, here in quantum computing, we need a more sophisticated mathematical framework, which is nothing but linear algebra. Right. So, the Boolean gate operation, we represent that as a Boolean algebra. Right. Here in quantum computing, the gates are represented as math. Right. So, this is polyexchange, or it is popularly called as gate. We have this matrix, which is 0, 1, and 1, 0. So, now when we apply, let's say we are applying get 0 as input. Let's say we are applying get 0. So, get 0 is applied as input. So, what is get 0? You know what is a get 0? It's a qubit which is 0. So, anything is represented as a unit vector in quantum. Imagine like in a say there are two possible values. So, you have to go for a 2D vector only. The possible 2D vector, so there should be two values. So, to represent 0 in a 2D vector, this 0 state is called as grounded state. We call them as grounded state in quantum computing. Which means but you can imagine spinning up. Spinning up is 0, spinning down is 1. So, the equivalent get 0 value in vector space is 1 and 0. Okay? When you have a get 0, this get 0 is represented in vector space as 1, 0. Get 1 is represented in vector space as 0, 1. You should understand this first. Rather than you will understand all these. So, get 0 is represented as a unit vector like this 1, 0. Get 1 is represented as a unit vector 0, 1. Why 1 in the first row here? Why 1 in the second row here? You could even swap it. The physics would still work. But globally, consistently, or the quantum standard is to follow the equivalent of get 0 is 1, 0 here, and the equivalent of get 1 is 0, 1 here. So, like when I remember this as visually 0 is spinning up. It is a grounded state. So, spinning up is the upper value will be 1, 1, and then in get 1 it is spinning down. So, the lower value will be 1. Okay. So, now let's apply get 0 and 2. So, you know that get 0's value is 1, 0. 1, 0 value is 0. And then take the expansion and then multiply the expansion. You know what is multiply it and this. So, you are again, and 1 by 1 is 1, plus 0 into 0 is 0, so we get 1. So we get 0, 1. So 0, 1 is the equivalent of get 1. Get 1 equals value to 0. So the output is get 1. So we apply get 0 and we got get 1 as 1. So when we apply get 1 as the input to this coordinates here, let's take the x matrix again, and then the equivalent of x 1 is 0 is 1. When you do the multiplication, you will get 1 0 as your output. So 1 0, what is the equivalent value 1 0 in the equation? It is get 0. So we get get 0. So we call it actually works like a capital not get. So if get 0 is applied, we are getting get 1. If get 1 is applied, we are getting get 0 not. Suppose if we apply the superposition, what is superposition? The superposition is alpha amount of get 0 plus beta amount of alpha get 0 plus beta superposition. So when we apply that superposition to the what would happen? So we would get this as well. So we get this coefficient. We will get beta 0 plus alpha 1. This would be. So when we apply generic probability scale to the x case, we get the coefficient. So this is how you can understand the get quantum. This is one more gate I'm taking. And gate. We cannot say that this is the equivalent quantum equivalent gate for the classical hand. Roughly this is equivalent. Just because the hand gate is having multiple inputs, I want this gate. So you know what is an AND gate? You execute the input and then the AND object is done, and then you take the output. So here there are multiple cubic states in the input, and we are taking multiple cubic states. Multiple cubic states. So multiple x we are applying, and multiple x we are going as output. Okay. So you know that the AND gate is not irreducible. You can't from the output I can't determine the inputs. Isn't it? From the DO, I can't determine what is D1 and D2. Maybe for multiple DOs, there could be different inputs. So the operation is not reverse. Whereas quantum gate operation is reverse. So when you apply setup to the Q1, Q2, Qn, you take Qn dash, Q dash, goes on to Qn dash. From the output state, you can always derive the quantum operation is reversible. That is the best thing about it. And one more important point to note is, if we have n inputs, there are certain inputs. So if there are n inputs, there are only n inputs. The input string is only n. It cannot be reached more than n. If there are 5 bits of given as input, you can take 1 bit of output. The input string is always 5. Whereas in quantum computing, if there are n x's given as input, you can always formulate 2 power n possible states, because quantum states are probabilistic in nature. There is no one determined state. It's all about probability. Therefore, the input state is 2 power n. If there are n qubits, you can formulate 2 power n qubits as inputs. So when the input is growing, then your computing is also growing. You do a lot of computation. So if you have some gates that can work in exponential size, because we are doing a lot of computation. Therefore, you have the functions that require exponential amount of computing is easier in quantum. So this is one part we do it. Okay. So far, I have covered the basis of quantum. What are the things you should know to understand quantum computing? The next one I'm trying to tell you is the notation. What is the notation that is being followed in quantum? There is some random algorithms in the net you might be able to understand. So the notation that is followed in quantum computing is called as Dirac notation, or it's called bracket notation. Okay, so so far you have understood what is the case. So characteristic, there's a bar and there's a symbol, and then you write inside here. This is called as characteristic most highest unit of object in quantum. This ket is used to represent a state. Sometimes the ket is used to represent a Curie purge. That's called ket. And you can understand this ket in vector space. In vector space, random vectors I and random vectors j can represent these states. And those are unit vectors. So in vector space, this ket are often used. In matrix space, we just saw that, right? So ket 0 is represented in a 2D vector space as 1, 0. You might ask why it is 2D vector space, why it is not 3D vector space, why it is not multidimensional space. Because there are only two possible values in combination, 0 and 1. At least you should have a 2D vector. If it is a 2D vector and it could be either 0, 1 or 1, 0. The standard notation of this followed in quantum computing is for ket 0, getting as 1, 0, and for ket 1, getting as 0. So this is called grounded state, and this is called excited state. You should remember these. So ket 1 is excited state and ket 0 is grounded state. In other words, ket 0 is spinning up, ket 1 is down. Okay. So when you write a general ket, so first I'm going to see what is ket 0, what is ket 1. If we write a general ket, okay. Only when we understand these notations, only when we understand what are these algorithms, what are the quantum-based concepts. When you study the concepts further, you could easily understand. Because if you go to ChatGPT or you go to any AI tool, if you go and ask what is quantum computing, they will immediately come up with concepts like what is entanglement, what is Indra Priyadharshini S. Any AI tool could tell us what is. But these notations, that would be a bit difficult to learn from internet. I thought of introducing these notations, quantum mechanics using these relations, and later we will go to the quantum concepts. That's the basic idea. So in the first session, I would like to introduce the various notations of these states. Second half is a set of theory, kind of talk, where I talk about quantum computing, what is the industry, the roadmap, all this stuff, the theory kind of stuff. So that like people who listen to the first session really well, using all this mathematics in the first session. Okay, let's get back. So this one, if it is general case, we will write it as a superposition statement, right? What is superposition statement? Alpha amount of 0 plus beta amount of 1. That would be a general. So you can imagine this in the vector notation. The alpha amount of vector I is beta amount of vector j. That can be in vector space. This ket psi is called psi. Ket psi is represented it's like a vector like this, and it is a as usual alpha and beta are complex coefficients. And we have something called as Hilbert space. In Hilbert space, the same thing in the form of matrix format is written like this, alpha and beta. And these are like linear combination of orthonormal basis space. We call that as orthonormal basis space. When you go and search what is an orthonormal basis space, there are certain properties for the quantum state to be. For example, it should be orthogonal. It should be normalized. You can go and search what is orthogonal property, what is normalization. Only those properties are followed, then it should be. So that is the concept of orthogonal basis space. And then what is Hilbert space? What could be Hilbert space? Okay, let's assume there is a plane, exactly right. So in this exact plane, let's say that there are two vectors. Vector I is aligned to x-axis and vector j is aligned to y-axis. So this is vector j and there is nice to be. I don't have a pen here, I have only this. So there is a I vector and there is a j vector. So y vector is aligned to the x-axis and j vector is aligned to the y-axis. Then we could plot any number of linear combination of this vector I and vector j in the xy plane. If I is aligned to this x-axis and j is aligned to this y-axis, then linear combination of whatever the coefficients of this I vector and j vector, we could plot it in xy plane, right? So this is the same xy plane, right? If it is extrapolated in 2D plane, it is xy plane is 2D. If this 2D plane is extrapolated with multiple dimensions, let's say there are multiple dimensions, there are multiple plotings going on. In that kind of space is called as Hilbert space. So that's to make you understand what is Hilbert space. Hilbert space is extrapolation of a 2D plane into multiple dimensions. All the coefficients of those plotted points are complex. That is called Hilbert. So in a Hilbert space, the matrix is represented like this. And the standard basis in an exact state is 0, 1. That's what I'm trying to tell you. So this direct notation, we have just learned what is a kit and how kit is represented in space, how kit is represented in matrix space, and then if you generate kit, how you can represent Hilbert space. That's what we just saw. Now I'm introducing the next. So now we have seen what is a kit. Now we want to see what is a kit. So when you look at the symbol of bra, the ket is like this. Ket is a bar and then there is cell and then whatever space inside is. When you look at the bra, it is just the opposite. It is like this. Right? So this bra is you can basically think of a bra as a function, okay, or like an operator. You can apply the bra to a ket. If you find it sounds a bit weird, just think of a bra as a function. You write a function, you will send arguments to the function, you write a program. In similar context, bra is like a function or an operator. That takes ket as an input. Okay. So bra just won't do the opposite of ket. It may dual of a ket. Okay. So when you apply a bra to a ket, the output you get is the conjugate transpose of ket. So to understand what is conjugate transpose, you should go to your max, high secondary max. So what is complex conjugate? Let's take this alpha. If this alpha is a complex number, the real part is A and then the imaginary part is B. To take this complex conjugate of this alpha, you just change the signature. Hope you remember that, right? We talked about when we complex conjugate of a complex number, we just keep the real part as itself and we will just negate the imaginary part. That's the complex conjugate. So when we come back to the bra part now, the bra is an operator that takes ket as an input. So if you apply bra to a ket operator, you would just take the complex conjugate of this. Okay, and then you will multiply it with the bra itself. So you just take the complex conjugate of 1 and you multiply it with the 0 vector, you will get the bra ket. Okay, so when you want to take complex conjugate of matrix, so if it is a vector, it will be. If it is a matrix, what do you do? If it is a matrix, first you have to calculate this transpose of the matrix, and then go to transpose of the matrix. For every element you transpose the matrix, calculate the complex conjugate of each element. So you, for example, this matrix A, this A darab can be calculated with, you take the transpose of A, take every element from the transpose A, take the complex conjugate for each element. That becomes the conjugate. So this you have to understand. So if you take this one, if you ask me to write the ket, we will write it like this: the alpha beta. This is a column vector. Whenever we represent ket in the form of a matrix, we will write them as a column vector. But whenever you represent bra as a matrix, you will write as a row vector. This you have to understand. So whenever we write ket as being matrix format, we will write it in the form of column. When you convert bra into a matrix format, we will write it as a row vector. This is one thing that when we understand equation problem. This you should take it into account. So We go to next one. So far we are only talking about zero get and one get when we discuss zero bra and one bra, right? So we will see how to represent bra in general, how to represent get in general. So to represent a get in general, if we write it like this, get is converted into matrix into vector. So you write as A1, A2, A1, then A, right? If it is bra, we will write as a row vector. We will write it as a row vector, and you know that all of them are complex numbers. So we understand. Hope this makes sense. If x 0, we will write as 1, 0, because it is a unit vector and it is a column vector, right? Because it is the bra 0, you will write it as a sorry. If it is bra 0, you write it as like this 1, 0, right? Because it is row vector. So similar way, so here we are writing as complex quantities of B1, B2, till B star, right? Now I will try to apply this bra operator to this get up. Let's try. So look at the symbol. So we have bra applied to this get up, right? So first we have to write bra, and then bra 5 I is applied to this I. So this is the symbol. So let's try to compute what is phi. Phi is B star, B star, and so that we will write it here. And then in the place of the psi, we will write this vector. Oh, sorry, we will write this column vector. A1, A2 goes on to n. Then we will go for multiplication. So when you multiply, what happens? B1 star in B1 plus B star in B. You take the entire row, you multiply with the entire column, you will get the scalar quantity. I mean, one whole number, one whole complex number that you will get as the order. So whenever you apply bra to one get, you will get the scalar quantity as the order. Then one complex number will be acquired as order. Yeah. This follow instead of this general expression. Next slide. We will apply an example. So we are going to apply law 0. You can see instead of phi and chi, let's substitute the states. Instead of phi, we are applying a 0, law 0. Instead of the phi, we are applying the ket 0. So we are applying law 0 to a ket 0. Okay, it's called bracket 0. It is called as bracket. Let's substitute this. In the place of 0, we will write 1 and apply it again. Instead of this phi, instead of this particular general thing, we are going to apply. Sorry. Yeah, we are going to apply 1. Equivalent of 0 and 1, right? We are going to apply 1 to 5. This is going to be vector, right? So bra 0 is applied to ket 0. So bra 0 we are substituting 1 0 here, and for the ket value we are substituting 1 0. So when you multiply what will be 1 plus 0 and 0, so we are getting 1 and 2. So bracket 0 0 we are getting 1 and 2. Okay. So similarly, we will try to apply bra 1 to get 0. So bra 1 to get 0. What is the equivalent of bra 1? What is the equivalent of 1? 1 is 0 1, right? Bra we write as the row vector, right? We write as the row. So we write row 1. And then the equivalent of 1 is, if it is bra, we will write it as row vector. The equivalent of 1 is 0 1. That is the and then ket 0. The ket 0 is 1 0 1. So ket 0 is 1 0. So when you multiply it, it's 0 is 1 0, then 1 0. So what we are actually doing, we are substituting the bra, which is a row vector, and we substitute the ket, which is the column vector. So when you multiply it, we will always get one scalar quantity of work, one complex number of output. So there is something called as Kedbra, which is the opposite of bra. Okay, first Ket will come and then we will apply it. So Ket is applied to the bra. So when Ket is applied to bra, you know Ket is the row vector. You have a row vector. What is a row? Sorry, you apply a Ket to the bra. Ket is the column vector. So we have this is the n rows, one column. Sorry, one column, but there are n rows in this case. But in the bra, there is only one row and there are n columns. Right? So when you multiply a Ket with a bra, you get n columns. So this bracket always gives us a scalar quantity also. We get one scalar quantity, one whole number or one complex number as well. But when we apply Kedbra, which is the opposite of bracket, we will always get matrix as well. That we should remember. That's why we call bracket as the operator. Bracket is the operator. Right? In general, I want to tell you this. This alpha and beta are called as probability amplitudes. They are not the actual probabilities, they are probability amplitudes. With these probability amplitudes, you can always calculate probability. How will you calculate probability? You will take mod of alpha and then you put square, that is the probability of zero. So when a quantum state can turn into a zero, that is alpha square. When you calculate alpha square, you get that. When a probability state can turn to 1, that can be calculated to a beta. So mod of beta square will be probability. So always this alpha square plus beta square is equal to 1 because it is probability. Right? So when you add up the probability, the probability is equal to 1. Right? So always you should remember that when you are studying algorithms, it would be equal. So probability is equal to alpha square, mod alpha square, probability is 1 is always mod beta square. So when you put alpha square plus beta square, 1. All this you can represent in polar coordinates using trigonometry in polar trigonometry. That's it. Okay. Right. So what are actually cubes? So we have so far considered right. The notation that is used in quantum computing. What is a quantum field? What is a field? What are here? And then why quantum states are probabilistic? How classical states are deterministic? This is what we see so far. So yeah. Okay. So now let's see.
Excuse me, madam.
Yes, sir.
Yeah, in your bracket operator,
Yes, sir.
is there your example gives only real number? Can you give me an example with a complex number as output?
That's what we did with this case, sir.
No,
Complex number
only no. Bracket operator
yes.
finally comes down to a complex number, no? In general, scalar.
Yeah.
So your example got only real number example.
Yeah. Because
Can you give me an example with a complex output?
Okay.
Because your inner product reduces, you put no single complex number.
Yes.
But your example is a pure real number.
Yeah. Because we took.
No. It's not a complex number.
Yeah. Because this I took the state as well. So I take it as state time. Then I have to just alpha turns to 0, beta turns to 1, and then I have to apply it. If I'm going to apply for this equation, if I apply Ket bracket, for example, if I'm taking this as my Ket, so I will get alpha 0 plus beta 1. And then if I'm going to apply bra for this, let's say I'm taking bra 0 for this scatter. Then I have to multiply 0, 1 0. It should be 1 0 multiplied with alpha beta. This entire equation can be represented as alpha. And then I have to go for a multiplication. So it will be 1 plus 0. It will be like this. The output will be like this. I hope it explained your question. Yeah, I think I can move on. Yes. This slide is also explaining. We are taking now this qubit as we are taking as alpha terms of 0 and beta terms of 1, which is a complex number. Alpha and beta are complex coefficients. So I told you if you can even represent complex number in polar coordinates, which is r into e power I theta. In this way also we can apply. So when we take mod for that, it would be when we square it. When we square it, we will get root of a square plus b square. When we square it, this exponential part gets discarded and then we will get r as the order. So if we are taking now that you will say that we are not taking 0 set or 1 set, we are taking this superposition state as the qubit. So how this qubit can be measured? How you can when, for example, if this is the qubit state, when it will come to the normal state, when it will come to the classical state, how you can measure that? That I have taken in this slide. So this is exactly answering this question. So we are taking So we are trying to take from 0. How much amount of probability is for 0? I mean, how much amount of probability is there for a cubic state to be turned into 0 state? That's what we are trying to check. So this is the problem for that. So we have to apply ket 0 to bra 0 to ket q, and then we should take mod and the whole square. This is the formula. So we are going to take to calculate the probability of 0 state. We are going to take bra 0 for the given ket, and then you have to square it. That's what we are going to do. So take write bra 0, and then we are just substituting the q value, which is the given superposition equation, alpha times of 0 plus beta times of 1, and then we are going to square it. Okay. So now what is bra 0? What is bra 0? Bra 0 is, we have to write it in terms of row vector, right? So that we are writing here. So let's try to group it now. Let's bring the alpha outside. Let's bring all the alpha outside, beta outside. So when you take the alpha outside, this is bra 0 applied to ket 0. And when you take beta outside, again this bra 0 will go inside. So bra 0 is applied to ket 1. If I'm not confusing it, I'll repeat again. See, we are going to calculate the probability of 0 for a given qubit q. When that qubit will go to 0 state. That's what we are trying to calculate. So to calculate that, the formula is we have to apply bra 0 for the given ket q. So we are writing bra 0, and then the given ket q is just written here. And I'm trying to bring out all the complex quantities one side, and then the scalar quantities inside. So alpha is taken out. So we are taking bra 0 inside. That should be applied to get 0 plus beta. And then bra 0 inside. And then get 1 comes there. Now you can go and just multiply. Substitute bra 0, this is 1 0. And then you know what is get 0, this is 1 0. So you will just multiply. You multiply this row by this column. And then what we get 1 into 1 is 1 plus 0 into 0 is 0. So this term is 1. This term it will be 1. So when you take beta now 0 is again 1 0. 1 is again 0 1. So it will be 1 0. And this will become 0 1. So now 1 into 0 is 0. 0 is 0. So this term will become 0. The whole term will become 0. This term will become 0, this term is 1. So only alpha squared remains. So to calculate how much amount of probability 1, how much amount of probability 1 given qubit state Q, we are going to apply bra 1 to the given qubit state Q. So bra 1 is written, and then you write whatever given equation directly here. And then this bra 1, we will take all the alpha quantities out. So alpha quantity bra 1 into 0, when bra 1 into get 0 plus beta into bra 1 into get 1. So when we apply now this, when you do the multiplication of bra 1 into get 0, bra 1 into get 1, you will see this quantity becoming 0. When you do this substitution and multiplication, you will see this term becoming 0 and this term becoming 1. So the remaining one is beta. So therefore, probability of 0 is alpha squared, probability of 1 is beta squared, this probability is add up to 1. That's what I'm trying to get. Yes. Okay. Okay. If you want, I can give you the polar quantities also, so that you can. Maybe you can work further if you want. I'm just giving you the polar quantity. Alpha 1 is equal to R1 into e to the power I theta 1. Theta 1. Beta is equal to R2 into, like, if you want to represent them in the form of polar quantities, like if you are coming from the electrical background, you can even know better than me. I into theta 2. This theta 1 and theta 2, the theta 1 theta 2, the difference between these two angles. And when the quantum state is rotating in between 0 and 1, that is the whole fundamental of quantum mechanics. This probability of rolling between 0 state and 1 state, you could visualize it in block scale. This is called block scale. So far we are seeing qubit in terms of mathematical paper. If you want to visualize it, it would be something like this. This theta 1, theta 2 difference, we call that as phase difference. We will call that as phase difference. So when you can understand this phase difference very well, then this applying a single qubit to various states of qubit, it would become very easy if you understand the difference between theta 1 minus theta 2 or the phase difference. So you have something called amplitude and phase. This alpha and beta called amplitude, I told you, right? Probability amplitudes. This theta 1 and theta 2 are called the difference between theta 1 and phase difference. So the entire quantum computing is running on this amplitude and phase. Okay. So to visualize the qubit, it's in this slide. This is not. So I was writing here. So here we have alpha 1 is equal to R1 e to the power I theta 1 and R2 power I theta 2, right? So this is nothing but alpha and beta. You know that alpha plus 1 is equal to 1. Same is written here. See, if you want to, want to represent this in the trigonometric form, they are taking R1 is equal to cos pi by 2. So I was wondering why they are not taking cos pi. That was my question when I saw this No, we know that constant of is times with equal to 1. If at all they want to transfer, replace that equation, why they are not taking as theta by theta by 2, I will consider. So, when we put theta to 0, okay, when we substitute theta as cos 0, yeah, we know that cos 0 is 1, right? And then, so this R2 will be 1. Then sin 0 is 0. So this part is negative. When we put theta as 0, right? So therefore, cos 0, then get this particular part as 1. Therefore, this particular full probability is 1. If alpha is full 1, then full probability is 0. So we are moving towards the upper part of the this is called not relative, not true. We are moving towards the not polarized. If we are putting theta is equal to 5, theta is 5. So cos pi by 2 is cos pi by 2 is 1, sin pi by 2 is 0. That case, you will get this part is cancelled out and then you will beta is. Therefore, we will move towards the output which will go to the network. I mean, what I'm trying to tell you is, we want the probability of put I as 0, we are moving towards the output value. We are putting I as 5. So moving towards the output of the we are moving towards the 1 state. And the probability is also that alpha is becoming 1 when we are moving towards the up, beta is becoming 1 when we are moving towards the down. Therefore, usually we can use this furnace block. So generally they are this instead of writing theta 1 and theta 2 for this alpha and beta, they just try to keep it as 1 as theta, but the other one as theta minus. This 5 becoming the phase difference. So when the phase difference, the phase difference is coming to the picture, the speed counts. If the phase difference is 0, you are moving towards the 1. So by this understanding, we can visualize the two blocks. Yeah. So I'm just taking the important points. There are a lot of points we need to write up. So we have already poly exchange is not okay. There's something called as poly exchange. Poly exchange is used to in the piece. I told you what is phase. If you want to move towards south, the phase should be negative. If you want to move towards the north, it should be positive. So if you want to shift the phase, you go for this poly exchange. So you get it, you get it also. When you apply 1 case to poly exchange, you get minus 1 load. So you are moving towards the south of the rotate around the zone is used for the case. And then something called as poly case. This is for the entire 180 rotation around the zone, which you can use. So any case you take the linear matrix, just like not this poly exchange is right, part of not case. Just like that case, for every day the linear matrix, and you will multiply that matrix, get and this giving you what is the factor of load. Poly get the case for this. Poly Y is for rotating around the load. And this is called a hardware create. Hardware create will create this superposition. We are talking about superposition, right? To create the superposition, we use hardware. So if I apply hardware create, you get this superposition. You apply hardware create to 0 state, you will be between 0 and 1. You apply hardware create to 1 state, you will be between 1 and 2. So it brings the superposition. You get any algorithm, sure algorithm, true algorithm. This is the basic on hardware theory. Here, important. Most times they use hardware theory exponent. So all these gates are working on physics. 1 qubit input, 1 qubit output. This hardware gate, poly Y gate, poly, all of them are single qubit. So if there is a 2 qubit or multi-qubit gate, that's called C0 gate and so there will be a control input. If the control input is 1, the target. If you put the target as 0, control bit as 0, there will be no change in output. If you give control bit as 1 and target bit as 0, then the target bit is 1. So if the control bit is 1, you will the target. For VCP target, there will be 2 control bits. There will be 2 control bits. 2 control bits, more than the control bits are 1, then it is the target. So these are some of the gates. So hard mud gate is for the deal of the phase gate and edge gate. Put together, phase gate and hard mud gate together, then make the interference. For entanglement, we will use T1. So like all the quantum elements will use these gates statistics to bring the effect. So if you go to IBM testing platform, just like plug and play components, you also use the Raman. We can just place the gears and construct quantum. And we can try to see the report, what is the state of the domain. We can test it using IBM. Yeah, I think that so the object of the question one is done. All the quantum field available, and then the how to visualize the qubit, what is the qubit, how to visualize it, and then what is direct, what is square, what is bra, what is not what is zebra, and then we compare classical and quantum understand what is quantum computing, and the motivation behind why should we learn quantum computing. This compares different types of algorithms available. Categorize why problems are hard, why it is not factored in testing, why we are moving towards quantum computing, and then why quantum computing is not able to solve all types of problems, all the ways. Hope it gave some idea about quantum computing. I think I can wind up with this and have a break and then start.
So, participants, if you have any queries in this quantum computing topic, you may ask.
Yeah.
So, you can post the queries in the chat, or else you can unmute yourself and you can interact with Dr. Indra Priyadharshini.
Excuse me, madam.
Yes, sir.
In classical computing, we say not and are. These three are functionally complete, no?
Yes, sir.
Any other circuit can be generated by these three fundamental operations. Similarly, in quantum computing, we have a functionally complete set of gates.
Okay, you're asking about just like input gate in classical computing, we have quantum. That's what you're saying.
Yeah.
Okay.
Yeah.
So, from my knowledge, there is no universal gate in quantum computing, but we could construct any type of circuit with a combination of H and T gates, Harman gate and T gate. This Harman gate, we don't have any classical equivalent technology because we cannot use in classical. There is no equivalent gate for Harman gate in classical. But we could construct any type of quantum system equivalent to classical with a combination of Harman and T gate.
Thank you, madam.
Yes, sir.
So, participants, if you have any more doubts, you may ask now. So, if no doubts are there, so thank you, ma'am, for your highly insightful and engaging session on quantum computing fundamentals for faculty, covering the concepts, algorithms, and pedagogy. Your clear explanations and practical perspective on quantum computing have greatly enriched our understanding from the basics, and I believe that it inspired our participants to explore this emerging field with confidence. And we, the organizing team as well as Department of CSE, deeply appreciate the time, effort, and expertise you have shared with us in this session. Thank you once again for being an integral part of our international FDP and for making this session one truly impactful. And participants, now we shall take a break for 15 minutes and have your refreshments, and we shall resume our session 2 by 7:40 p.m. So please ensure that you are back online on the stipulated time and ready to continue with the sessions. So we shall have a break and we shall resume by 7:40 p.m. Thank you.